Hello, in this video we are continuing our discussion of section 7.7 on differential equations. Specifically in this lecture we are talking about logistic growth. So this is something that can be used to model the growth of populations. If we have a differential equation of the form dy dt is equal to k times y times m minus y, where k and m are constants. K is considered to be the growth rate and M is a carrying capacity, so it would be something like the maximum population, and K would be indicative of how quickly or slowly the population grows. If you have a solution to an equation like this, then the solution, the function, grows logistically, so we have something that is pretty good for predicting population growth. So in example 2, we have the differential equation dp dt equals 0.001p times 1000 minus p, and p of 0 is 100. In part A, we're asked to find the solution of this initial value problem, and then in parts B, C, and D we're going to use this solution to complete a few different parts. But first we need to solve the differential equation. Now the lecture mentioned that these sorts of equations are separable, and the solution of the well, in the lecture it described it as the y side. Here we're going to have the p side. It's going to need a partial fraction decomposition to solve. Now I could very well take this whole thing to the left hand side because there's no t's here, but I'm going to go ahead and leave this constant 0.01 on the right just because it actually makes the integration a little bit easier. So I'm going to have dp over p times 1000 minus p, and that's equal to 0.001 times dt. So then we integrate both sides. On the right hand side, this is very easily equal to 0.01t plus our constant c. The left hand side, we are going to need a partial fraction decomposition. So I'm going to look at 1 over p times 1000 minus p. We have two factors here, they're both linear, so I'm going to have an a over p plus b over 1000 minus p. Then multiplying through by our denominator, we'll get a 1 on the left. On the right, I'm going to have the p cancel out for that first term, so I'll have a times 1000 minus p, plus b, the 1000 minus p will cancel there, so we'll have b times p. If we rewrite the right hand side, we'll get a times 1000 plus b minus a times p, and that's equal to 1. So then this means that 1000 times a equals 1, and b minus a equals 0. So a equals 1000, and b equals a, sorry, that's a 1 over 1000. b equals a, which is also 1 over 1000. So what this means then is the integral of dp over p times 1000 minus p is equal to the integral of 1 over 1000, that's our a value, over p dp, plus the integral of 1 over 1000 over 1000 minus p dp. We'll have 1 over 1000 integral of dp over p plus 1 over 1000 integral of dp, sorry, my p's are degenerating into d's, dp over 1000 minus p. So this first integral is very easily recognizable as the natural log absolute value of p. The second integral, you might want to do a quick u substitution. U is 1000 minus p, so then du is going to be negative dp, so we'll have that negative to account for. This will end up giving us a p minus 1 over 1,000 natural log absolute value of 1,000 minus p, where this negative here came from the u substitution. Okay. All right, so this is what we have on the left-hand side. I'm going to go ahead and simplify this a little. We have 1 over 1,000 times both of our terms, the natural log absolute value of p minus natural log absolute value of 1,000 minus p, and then if we use some properties of logarithms, we can write this as the natural log absolute value of p over 1,000 minus p. So if we take this and substitute it back in here on the left-hand side and write our right-hand side as that, we are going to have 1 over 1,000 natural log absolute value of p over 1,000 minus p, and this is equal to 0.001 t plus c. Now I want to solve for p so that I can get p as a function of t. So I'm going to multiply both sides by 1,000, so I get natural log of p over 1,000 minus p. This is equal to t plus 1,000c. I'm going to go ahead and write that as a k. If you want to just rewrite this as c or c hat or whatever, that is perfectly fine as well. Now I'm going to exponentiate both sides, so that means I'm going to take e2 and raise it to both sides, so we get p over 1,000 minus p because it cancels out with the natural log. This is equal to e to the t plus k. Now, multiplying both sides by 1,000 minus p, I will get p equals e to the t plus k times 1,000 minus p. And actually, before we go any further, we can do a little bit more to simplify what we have written here. This is equal to e to the t times e to the k, and since k is a constant, this is just another constant. Let's say, I don't know, c hat. Okay, so this is equal to a constant c hat times e to the t, and that's how that is written a lot more often. So we would have c hat e to the t. Again, if you just had this written as a c e to the t, I would not count off any points there because that's what ends up being done a lot in practice. So now this is just a little bit easier to write. We have c hat e to the t times 1,000 minus c hat e to the t times p. I'm going to take both of my p terms to the left, so I have p plus c hat e to the t times p. This is equal to 1,000 c hat e to the t. Factoring a p out on the left, 1 plus c hat e to the t. This is equal to 1,000 c hat e to the t. So we finally get our function p of t is equal to 1,000 c hat e to the t over 1 plus c hat e to the t. So this is our solution. This is a general solution. We call this general because of the fact that we haven't used the initial condition yet to find our specific solution to the initial value problem. So then using that next, we have that p of 0 is equal to 100. If we plug in 0 for t here, that goes e to the 0 is 1, e to the 0 is 1. So we end up with 1,000 c hat over 1 plus c hat. You can do some arithmetic here. You essentially end up reversing a lot of the steps that you have just completed up to here, so that you end up getting that c hat will be, let's see, what was it? 100 over 1000 minus 100. There we go. So that's going to end up simplifying to 1/9. Okay, if we reverse these steps up to this point, divide through, yes, actually, if we reverse back up to this point here, you can substitute in a 0 for the t, so you end up getting c hat is equal to p, which is a 100 over 1000 minus p, which is 100, and there we go. So 1/9. All right, so then the solution to the IVP, the initial value problem, is going to be p of t equaling, what do we have? 1000 times 1/9 e to the t over 1 plus 1/9 e to the t. And just to make it a little bit nicer, let's simplify this so we get 1000 e to the t over 9 plus e to the t. So there's our solution. Now, one thing to note, in practice, these sorts of solutions for population a lot of times are rewritten so that you only end up with an exponential in one term. And the way this is done is by multiplying numerator and denominator by e to the negative t, so that you end up getting something like the population being 1000 over 9 e to the negative t plus 1. Okay, the reason why it's written like this is it's a little bit easier to work with this since you only have one exponential function. It's also a bit easier written in this form to figure out what the end term behavior is, which is something that we will do in part D. Okay, so now let's talk about part B. Part B, we need to find the population after 1 year. So this means we are going to plug 1 into t, so we can do it into this form here, 1000 e to the first over 9 plus e to the first, or we can do it in the rewritten form, 1000 over 9 e to the negative 1 plus 1. Either way, they are equivalent values, the exact values there if we get some decimal approximations, and we're talking about a population here, so let's round to the whole number. So we get 232. Any of those answers would be perfectly fine for part B. In part C, we have been asked to find what t value the population reaches 900. So we're talking about what t value does the population equal 900. So this means that we're going to plug in 900 for p. I am going to go ahead and use the rewritten formulation so that we only have one t that we have to solve for. So we have 900 equals 1000 over 9 e to the negative t plus 1. And then to solve there, let's see, we will get, if we multiply both sides by the 9 e to the negative t plus 1, we'll get 8100 e to the negative t plus 900 equals 1000. 8100 e to the negative t equals 100. Now I'm going to divide both sides by e to the negative t so that I get e to the t, or 100 e to the t, equals 8100. Dividing both sides by 100, we get 81 equals e to the t. So then t equals the natural log of 81, and if we find an approximate value here, we'll get about 4.39, and we do have that time is measured in years. So you can give the exact value, the natural log of 81, or you can give the decimal value 4.39. Either way, you do need to label it in years. So it will take us a little less than 4.5 years in order for the population to get up to 900. The last part of this problem is part D, and that asks us what the long-term population behavior is. In other words, what is the limit as t approaches infinity of p of t? Now we can evaluate the limit as t approaches infinity of the first way that we had written the population. So that was, let's see, 1000 e to the t over 9 plus e to the t. But this is when it really comes in handy to use that other way of writing it, which was 1000 over 9 e to the negative t plus 1. Now the reason for this is there's only one term with a t in it. So the limit can be pulled in here, so that we get 1000 over 9 times the limit as t approaches infinity of e to the negative t plus 1. Now, since this is a negative exponential, as t approaches infinity, the exponential function goes to 0. So we end up with 1000 over 9 times 0 plus 1, or very simply just 1000. So the long-term behavior of this population then is 1000, meaning that as time increases, it doesn't matter how far it goes on, the population will eventually end up at 1000. Now if you recall, this 1000 was denoted with an m in the general logistic growth differential equation. That m was a carrying capacity, which is meant to be a capacity that the population does not increase, does not pass, or if it does pass, then it decreases down to this population. So in other words, the long-term behavior of this population solution, will always end up being this carrying capacity value here. So for part D in this example, the limit as t approaches infinity of p of t is 1000. You can write it that way, or you could say that the long-term population is 1000. And that finishes up this example, which also completes our lecture for differential equations.